Yeah, until now we studied the magnetism and magnetic materials. From now on, we are going on to study the physics of superconductivity. Anyway, the superconductivity is related to with magnetism and magnetic materials because the superconductivity also deals with a spin. Then what is a superconductor? You know, the superconductor has you should know that there are two characteristics in superconductivity. One is that zero resistance, zero electrical resistance. The other one is that perfect diamagnetism. We call it is the Meissner Effect. Meissner is the name of the name of the physicist, and it is a perfect magnetic flux explosion. And if we find that two characteristics, zero electrical resistance and perfect diamagnetism, we can say that it is a superconductor. And a superconductor has a zero electrical resistance below a certain critical temperature, and superconductivity is occurred at a low temperature. We call the transition point is a TC, critical temperature. Once set in motion, a persistent electric current will flow in the superconducting loop forever without any power loss. And in general, metallic wire like copper or silver, platinum, and when you apply the electrical current and turn off the electrical bias, the electrical current density also disappeared. But in superconductor, and when you apply the electrical bias in a enclosed circular loop, and there is a persistent current forever without any power loss. It is zero characteristic of the zero resistance. And also, second characteristic is the perfect diamagnetism is that superconductor excludes any magnetic field that come near it. And here, this illustration, this picture shows that the Meissner effect, and the below one is the magnet. For example, when you apply the magnetic field in the permanent magnet, it is a magnetic field, and the magnetic field cannot penetrate to the superconducting materials, and it excludes the magnetic field outside like this, and therefore in low case there is a high magnetic field energy, and in the upper part is magnetic field energy is low because magnetic field energy gradient, and there is levitation. We call it is this levitation is due to the Meissner effect. And here, when we measure the electrical resistance and versus temperature, and it is in this case, this one is a YBCO sample yttrium barium calcium copper oxide. It is high TC superconducting state, and with a decreasing temperature, electrical resistivity decreases monotonically, and at certain temperature, we call it a TC, the electrical resistance significantly drops at zero electrical resistance. It is a zero resistance. We call it as perfect conductivity. And the lifetime of the persistent current is theoretically predicted and experimentally confirmed that it is 10 to the 5 years. Very 0.5 million years, and a very long lifetime. And also theoretically, the persistent current can persist forever, 10 to 10 years, and it is if the sample does not degrade. And below the critical temperature, magnetic field is excluded, and therefore it is we call it is a magnetic levitation. It is Meissner effect. And there is a critical field, magnetic field, destroy the state of superconductivity. For example, in type, there are two kinds of superconductivity. One is the type 1 superconductivity. The other one is the type 2 superconductivity. Type 1 superconductivity, this superconducting state breaks down abruptly in a certain point. When we apply the temperature, when you increase the temperature, at certain temperature, destroy the superconducting state. Superconductor becomes normal state at certain temperature. But in here, when you apply magnetic field, at certain critical field, we call it as a BC critical field, the superconducting state breaks down and it becomes a normal state. But in type 1 superconductivity, and when you increase magnetic field at some critical field, there is two critical fields. One is that lower critical field. The other one is the high critical field. Lower critical field is that the penetrating field. It is a field that penetrates the magnetic flux into the superconducting sample. If the magnetic flux, we call it as quantized magnetic flux, can penetrate into the sample, and we call it as a BC, lower BC1, lower critical field, and BC2 is the upper critical field. Upper critical field totally breaks down a superconducting state, and it becomes a normal matter. And therefore, there are two critical fields. One is that the lower critical field, the other one is the upper critical field, and it is type 2 superconductivity. Here the condensation energy I will describe later for detailed calculation in terms of London theory. And the condensation energy is the energy difference between the normal state and superconducting state. And basically, why the superconductivity persists, that is that in terms of thermodynamic point of view, the superconducting Gibbs free energy is lower than the normal state metal Gibbs free energy. And therefore, also there is a critical field energy. It is a field energy, Hc squared over 8 pi. It is a critical field energy, and we will discuss later in detail. When you see the periodic table, and this yellow one is the superconducting elements, and there are many superconducting elements like beryllium, titanium, vanadium, and many transition metal materials show the superconductivity. But the non-superconducting, the green one is a superconducting materials only under certain condition, like when you apply the pressure by making a thin film, and it shows the superconductivity. And when you see detail in here, and here it is inert gas. Inert gas is not a superconductor, and also magnetic materials are not superconductor because it is magnetic materials and mangan, cobalt. It is cobalt nickel. Cobalt nickel is magnetic materials, but iron also magnetic material. Iron, chrome also magnetic materials. But when you apply the pressure for iron for 21 gigapascal, it becomes a superconductor 2 Kelvin. In the chrome case, by synthesizing a thin film, it becomes a superconductor 3 Kelvin. And anyway, here is the magnetic materials at room temperature, normal pressure, and bulk materials. In this magnetic materials is not a superconductor. And also copper, silver, gold, and platinum. It is very high purity metallic materials. Because copper, silver, gold shows that very low intrinsic electrical resistivity. and very low electrical resistivity is not a very clean metallic material is not a superconductor. For example, in this case, palladium also very pure sample, very pure, very low electrical resistivity materials, but it also the palladium showed a superconductivity on the irradiation. Some ion irradiation becomes the superconductor, but in normal condition, like a bulk sample and under there is when you apply there is no external pressure condition, and the very high metallic materials, copper, silver, gold, platinum, palladium, we call it is a noble materials. Noble metals do not show the superconductivity. And also rhodium, iridium, osmium, ruthenium is also very noble metal. Noble metals, the superconducting Tc is very low, about below the 1 Kelvin. And the tungsten and tantalum. And anyway, when we see that these many materials show the superconductivity anyway, and therefore then you do not need to remember this periodic table, but we should remind that small magnetic impurity breaks the superconductivity, and the magnetism competes with the superconducting state. I will discuss later why the magnetic materials break down the superconductivity. And basically, superconductivity is a Bose condensation. There is a fermions and the bosons. Electrons are fermions and have the spin, and the spin 1/2 spin, whether plus minus 1 spin, and down spin, up spin can be separated, and also ferromagnetic fermions is fermionic particle have the half integer spin. In bosons have the integer spin, but in boson case is that there is a Bose condensation. Bose-Einstein condensation. Bose-Einstein condensation is that all the particles have the certain energy state simultaneously. Then basically the superconducting state is kind of Bose-Einstein condensation, because all the super electrons, I mean all the super electrons have the same kinetic energy, and the flow, there is no dissipation. There is no dissipation. It means that all particles have the same kinetic energy, and therefore it is kind of Bose condensation. In order to have the Bose condensation, the spin state should be integer spin. Then therefore the two electrons should combine with each other. For example, in the superconducting state, and the spin up down has coupled with each other. Therefore the total spin is 0. Because total spin is 0, and the Bose-Einstein condensation can be possible, and that's why it is at macroscopic. Therefore the superconductivity is a macroscopic quantum phenomena. And also in here, that's why the magnetic materials has a positive spin. We call it is the fermionic particles, and the fermionic spin triplet state, and the spin singlet state. Triplet state is that spin triplet state breaks the spin singlet state, because super electrons has a spin singlet state, like a spin up down couple, spin up down coupling, and it is a spin singlet state. And the spin singlet state and the spin triplet state compete with each other. Therefore their magnetic materials break down the superconducting state. And the 1/2 pure metals show the superconductivity. One example, and there are aluminum 1.1 Kelvin, gallium 1 Kelvin, indium 3.4 Kelvin, tin 3.7 Kelvin, thallium 2.4 Kelvin, lead 7.2 Kelvin, like this, and also vanadium 5.4 Kelvin, and niobium 9.25 Kelvin, like this, tantalum 4.4 Kelvin. Many won't have pure metals show superconductivity. Many metallic materials exhibit superconductivity, and a pure material exhibits sharp transition, and like electrical resistance becomes that zero resistance. This transition is very sharp. There is no fundamental reason why all metals don't have superconductivity even at near zero temperature. And also for basic for fundamental theory for the superconductivity is the Bcs superconductivity will be dealt with later, and from the Bcs theory describe the formation of the Cooper pair like a spin singular state, and as well as that many the fundamental regions to form the superconducting state. And anyway, then there is no fundamental reasons why all metals don't have the superconductivity even at zero temperature. And let me see the perfect diamagnetism. In a superconductor, there is no magnetic field inside the superconducting materials. For example, when you apply the magnetic field like this, and the total flux expelled to the outside of sample, and therefore then in many cases when in many cases there are two types of superconductivity. One is the type 1, the other one is the type 2. And the type 1 superconductivity is that perfect diamagnetism for the whole sample. And in this case, this is type 1 superconductivity. And anyway, and we can understand that this phenomena as two separate cases. One is that when you apply magnetic field, and the uniform applied magnetic field can be considered like this, but why the magnetic field expels to the outside is that the negative magnetic field generating inside the sample. We call it induced magnetic dipole moment, and induced from the Lenz law. You know the Lenz law in electrostatics, where the electricity and magnetism, and the Lenz law do not favor to enter the magnetic field energy, and they'd like to expel the applied magnetic field also. And it is kind of persistent Lenz law. And until magnetic field induced, there is an induced persistent current expel the magnetic field inside a sample. And for example, and when there is a persistent current for the superconducting state, and it generating the negative magnetization, and the negative magnetization induces the zero magnetic field inside the sample from like the Lenz law. And therefore, and from B field is a summation for the applied field plus magnetization, because it is a zero inside the sample, and therefore magnetization inside the sample exactly equals to the minus HA. HA is the applied magnetic field. Therefore, from the definition of the magnetic susceptibility for the DC magnetic susceptibility is that M over H becomes -1 in the MKS unit. Yeah. And I will briefly describe the history of superconductivity. And superconductivity is observed in the 1911, and at that time there were debating how about the electrical resistivity at low temperature. And the Kelvin predicted that at low temperature the electrical resistance should rise like this. Why? Because Kelvin thought that metal there are many electrons, and at low temperature, because the freezing of electron, like ground state electrons, and because the kinetic energy becomes lower and lower, and it means that the velocity of electrons decreases. That's why the electrical resistance may increase. But in other words, Dewar say that the electrical resistance becomes close to zero at low temperature, because Dewar thought that because there is electron-phonon interaction, and electron-phonon interaction is significant in the metallic materials also at low temperature, and phonon vibration becomes weak, and therefore decrease of electron-phonon interaction, and may have the more free electrons, and that's why the electrical resistance may approach it to zero. Meissner predicted that say that there is electrical resistance may have the finite value at low temperature, because there are many impurities and imperfections, and the scattering of carriers may have the finite electrical resistance at low temperature. And therefore, at that time, it was an issue, how about the electrical resistance at low temperature? And here, Dewar, in order to measure the physical properties at low temperature, and the low temperature condition is very important. But how to decrease the temperature of the sample, and therefore, at that time, then the low temperature physics developed very well. And Dewar succeed to liquefying the hydrogen, and because liquefying hydrogen, the temperature is about 20 Kelvin, and therefore, by applying pressure, and hydrogen becomes liquefied, and the liquid hydrogen, the temperature is about 20 Kelvin. Therefore, the low temperature can be succeed. And later, Onnes in Netherlands found that he also succeeded to liquefying the liquid helium. And the helium, the liquefying temperature is about 4 Kelvin. 4 Kelvin is very low temperature at that time. And by applying the pressure of the helium, and he succeeded to achieve the low temperature for 4 Kelvin by using the liquefying helium. And after succeeding the liquefying helium, he measured various metallic materials. At first, I do not know why he measured the mercury at first, but he measured the mercury, and the transition temperature is about 4.2 Kelvin. And it is very fortunate, because the temperature for liquefying liquid helium reaches about 4 Kelvin, but in the mercury, the TC is about 4.2 Kelvin, and it is barely can identify the superconducting state. But when the Onnes used the other metals like aluminum or the gallium and indium, thallium, other elements, that the TC is below the 4 Kelvin. But fortunately, he used the mercury, and mercury is the TC. Mercury TC is about 4.2 Kelvin. Yeah, 4.15 Kelvin, and it is fortunate to measure the mercury on the sample. And anyway, later he measured the various materials like tin, cadmium, lead, and thallium later, and the superconducting state is found at low temperature. And after finding this superconductivity, he awarded Nobel Prize in the 1913, and just only 2 years later, he found the superconductivity. He found the superconductivity in 1911, but 2 years later, he got the Nobel Prize. It is very rapid awarding the Nobel Prize. And here is Van der Waals. Van der Waals is theoretical physicist and Onnes is experimental physicist. And in the experimental lab of Onnes, there was a very good technician, great film, and he established these low temperature facilities. And because of the low temperature facilities, and he succeeded to make a low temperature environment. And later, in the 1933, and Meissner and Ochsenfeld found another property of the superconductivity. It is perfect diamagnetism. And they found that the superconductor perfectly expelled the magnetic field. Above TC, the magnetic field penetrating sample, but below the critical temperature, superconductor expels the magnetic field, and also from inside the magnetic field should be zero. Therefore, the magnetic magnetic susceptibility is -1 in perfect we call it is a perfect diamagnetism. And there is a difference between the perfect conductor and the perfect diamagnetism. And here let me see that in a perfect conductor, and this is a perfect conductor, and when you cool down the sample, and you cool down the sample, and there is a field energy. Field energy is about 0, but when you increase the magnetic field, then the magnetic field expels, because then from the Lenz's law, they do not favor to enter the magnetic field energy, and therefore expel the magnetic field in the perfect conductor from the Lenz's law. After that, it is a very short time, but for long-lasting case, and anyway, it is magnetic field zero energy. Magnetic field energy still zero in the even though we apply the magnetic field. But in different case, we call it as zero field cooling case. Zero field cooling process. And in the conductor, a perfect conductor, and here at first, we apply the magnetic field. We call it as a field cooling. A field cooling process is that apply the magnetic field, then the magnetic field energy is not zero, finite magnetic field energy, and cool down the sample, and the field energy may have they favor inside the sample. They'd like to make a field energy, even though the switch off the magnetic field. By the switching off the magnetic field and the persistence magnetic field, they'd like to persist the magnetic field. Therefore, the zero field cool case, there is the there is no magnetization inside the sample. And in the field cooled case, and still do not change the before and after. And it is perfect conductor case. How about the perfect diamagnetism? Perfect diamagnetism in the superconducting state. Anyway, I say that it is the type 1 superconductivity. And the cool down case, zero field cooling process, of cooling first, and applying magnetic field, then switching off, then also still expels magnetic field. But in the different thing is that the field cool case. In the field cooling, at first increase the magnetic field, then cool down, still expel the magnetic field. And it is always magnetization is a negative magnetization. Magnetic, it always susceptibility is -1 in the perfect diamagnetic materials. But in this case, for field cooling, in the perfect conductor case, there is no difference between the magnetic field turn on and turn off. And it is significant differences between the perfect conductor and perfect diamagnetism. Therefore, in reality, there is no sample for perfect conductor because solid state always contains the impurities or imperfections, and there are electronic scattering, carrier scattering, and therefore there is no perfect conductor in this case. And anyway, in some cases, ideally, it is ideal comparison between the perfect conductor and the superconducting state. And therefore, we can say that the Meissner effect is more powerful investigation for the superconductivity because Meissner effect is more powerful, more fundamental property for the superconducting state. And perfect conductor also the electrical resistance is zero at low temperature also. I already say that there are two kinds of superconductor. One is the type 1 superconductor, the other one is the type 2 superconductor case. And the type 1 superconductor is the perfect superconductor for the whole sample. When a superconductor setting or superconducting state at a critical temperature, magnetic field is abruptly excluded a certain applied magnetic field strength. We call it is a critical magnetic field. At critical magnetic field, and here this is a superconducting state breaks down significantly, abruptly. Superconducting state breaks down abruptly, becomes a normal state. We call it is superconducting quenching of a superconducting state. It is the type 1 superconductor. But in type 2 superconductor case, a quantized magnetic flux, we call it as magnetic vortex. In the quantized magnetic field, it is magnetic field is quantized phi 0, and the quantized magnetic field penetrates into the sample, and there is an intermediate or a mixed state. It is a mixed state or an intermediate state. At low temperature and the low magnetic field, it is a perfect superconducting state. It is a Meissner state, perfect superconductor. But at certain critical field, lower critical field, in low critical field, and the magnetic flux, one magnetic flux penetrate the sample, but increased magnetic field, and there are the number of vortices. The number of vortices increases more and more by increasing the magnetic field. At some upper critical field, the superconducting state breaks down, and all the sample governed by the magnetic field, and it penetrates. It becomes a normal state. We call it as HC2, upper critical field. And when a current is applied to a type 1 superconductor in the mixed state, the magnetic vortex feels the Lorentz force. Magnetic vortex feels the Lorentz force that pushes the vortex at a right angle to the current flow, and the movement dissipates energy and produces finite electrical resistance. And also in here it means that when we apply the current, and current, there is a flux motion. We can use a flux. There is a flux motion, and with the carrier scattering by the flux motion have the finite electrical resistance, not absolute zero electrical resistance. And the representative material for the type 2 superconductivity is the high Tc superconducting materials. High Tc is observed in the lanthanum barium copper oxide, in the lanthanum barium copper oxide is a type 2 superconductivity. One is that the oxide cuprate superconductivity is observed in the I don't remember the exact year, but before that, mercury Onnes found that mercury becomes the superconductor, and the lead, niobium carbide, and niobium nitride, vanadium silicide, niobium tin, and niobium germanium is a well-known superconducting materials because it is the highest Tc value for the metallic materials. Therefore, in the metallic materials, we can make a wire, whether the wire and the deformation can be easily possible, and therefore the contemporary NMR system, what a superconducting magnet is made by the niobium tin or the niobium germanium. And but in high Tc, from the Bcs theory, I say that the Bcs theory is a fundamental theory for superconductivity. Bcs theory predicted that the value there is a barrier to have the superconducting state. It is not possible to. It is not possible. I mean that it is very difficult to make a superconductivity above the 30 Kelvin. And it is a result of a Bcs theory. But after later, in the lanthanum barium copper oxide is the very dirty materials, like ceramic materials. Ceramic materials is electrically dirty, and also it showed a very high Tc. We call it as a high Tc starting point for the high Tc because it exceeds the prediction of a Bcs theory. After that, YbCO and the bismuth cuprate and thallium and the mercury cuprate superconductor was found that, and also Tc significantly increases more and more, and up to now the Tc is about 160 Kelvin for the cuprate superconductor. But nowadays it is very old-fashioned data, and nowadays there is a report on the room temperature superconductivity. And like in the lithium, lanthanum, hydrogen, and hydride materials exhibited room temperature superconductivity. But the room temperature superconductivity only at high pressure, and high pressure is very difficult to available to use that practical applications, and therefore until now without applied pressure, it's about 136 Kelvin is the highest temperature for the superconductivity at normal pressure. And it is a mercury-based superconductor. And the crystal structure of high Tc cuprate material is that the copper oxide plane interspaced in the barium is a barium and the yttrium, and it is a layered structure, and it is say that there is a charge reservoir. It is a barium layer is a charge reservoir layer, and donates the electron or hole to the copper oxide plane, and the copper oxide plane is a superconducting layer. It is well known for the two-dimensional layered structure of the high Tc case. Many people say that understanding on the mechanism of high Tc superconductivity is one of the ultimate goals of condensed matter physics. because this high TC cuprate is very complicated physics, because there is a very profound physics in the phase diagram, like doping and temperature at the ground state. The ground state and the parent compound is the antiferromagnetic multi-insulator. It is a multi-insulator by making the hole doping. By making hole doping, there is a spin glass system and a pseudo gap. Pseudo gap is not a real gap, but a pseudo gap is very difficult to understand. And anyway, real superconductivity is observed as certain optimal doping region. At the high doping region, in the Fermi liquid theory is a conventional metallic materials in a conventional normal state, but in the vicinity of the superconducting state at high temperature, it is a non-Fermi liquid system. Non-Fermi liquid is deviating from the Fermi liquid. Fermi liquid is the theory is developed by the Ginsburg-Landau. Landau described the electrical resistance may have the quadratic temperature dependence and also finite magnetic susceptibility and specific heat, and it is a conventional in conventional properties in the normal state materials, and also but in TC, in the high TC material case, at the high temperature, a high temperature greater than the TC, the normal state property do not follow the conventional Fermi liquid theory. We call it is a non-Fermi liquid behavior. And there are many techniques to induce the superconductivity, like pressure and charge doping and proximity. Proximity is that in thin film and the superconducting state and the normal metal interface may have the superconducting state in the vicinity of the phase grain boundary between the superconducting state and the normal state, and the superconducting state penetrate into the normal metal layer. It is a proximity effect. And the structural phase, and by using the epitaxial thin films may generate that strain field with a different crystal structure, and strain field increases the TC, whether making the superconducting state. And also there is also amorphous superconductivity, and also irradiation induced superconductivity. Ion irradiation also generates that charge carriers, whether various superconducting mechanisms in this case. And there are several properties for superconducting state. One is the penetration depth. Penetration depth is that the length scale to penetrate magnetic field. And from the London theory, or the Ginsburg-Landau theory, and I will describe later, and when you apply the magnetic field, the magnetic field strength exponentially decreases like this. And therefore, it is the decreasing length scale. It is called the penetration depth. Here, the penetration depth depends on the impurities, and if the impurity concentration increases, the penetration depth also increase. And the measurement of this penetration depth is the direct measurement method is the μSR, muon spin resonance, or the frequency modulated magnetic force microscopy. And there are several methods to direct measurement of the penetration depths. Also, from the theoretical interpretation by comparing with the experimental transport or magnetic properties, we can estimate that the penetration depth also, but it is not a direct method but the indirect method by comparing the experiment and the theory. And the London theory, I will describe the London theory later. And in this time, we briefly introduced the basic property of the superconductivity and a brief historical overview of superconductivity. Nowadays, there is they reported the room temperature superconductivity, but under high pressure.